Hello, I am Olivia Sardina and welcome to my Capstone project. For my project, I'm building an induction heater circuit. This is an inverter circuit which uses DC voltage and turns it into AC output voltage. The AC output allows current to be induced in a coil, which can heat up conductive material when placed in it. My mentor for this project was my great-uncle Tom Henry, who is a retired civil engineer. He contacted his friend Mark Moore, who is a retired electrical engineer, who introduced me to LT Spice and helped me get started with it. The purpose of this project is to demonstrate concepts of electromagnetism, specifically induced current, through an electric circuit and get a better understanding of such concepts applied to real life. Learning from applying knowledge from school in real life is extremely important and will help me get a better outcome of learning. Learning from trying something myself will leave me with a more memorable experience that uses critical thinking to understand how things work, rather than only practicing using ideal situations in theory. Many people do not have access to apply the knowledge by building circuits due to components being inaccessible for price or other circumstances, and demonstrating my concept through a video with an explanation can help people who are unable to build a circuit on their own have a better understanding of the knowledge applied, and maybe even inspire other people to build one similar themselves. This is what the finished product looks like. This is the first schematic that I came up with. And this is the final one that I used to build my product. As you can see, 2 more diodes have been added, which are Schottky diodes. These are an important part of the oscillator because they have fast switching speeds, allowing the MOSFETs to switch faster and keeping losses low. In this simulation, 24 volts are being supplied, and as you can see, I read here, the current on this inductor L3 is almost 30 amps and the voltage is around 75 volts. There are also 2 decoupling capacitors next to the power supply, which I ended up not adding to my finished product because I didn't need it. The inspiration for my idea was several YouTube videos of small induction heater circuits and my interest in actual induction heaters. My original inquiry question was, how does alternating current cause metal to heat up when moving around in a solenoid? One of my first ideas was to demonstrate how induction heating works, since it has been a topic of recent interest to me, so I wanted to create an educational video on how induction heating works. I decided I wanted to challenge myself and build an electric circuit, so I came up with a way to model induction heating on a much smaller scale. My new and finalized inquiry question is, how can DC voltage be used to generate a changing magnetic field in a solenoid? The way it works is, it contains an inverter circuit which converts DC voltage to AC using a self-resonant oscillation system of 2 MOSFETs, 2 Zener diodes, 2 Schottky diodes, and capacitors. This allows the solenoid work coil to have induced current and therefore induce current in conductive materials. The goal of this project was to use the simulations on LT Spice to figure out the parameters and requirements for values that the components need, and then put together a list of the components to build the circuit. The way I did it was using this soldering iron to connect the components. I put some components on a prototype board for neatness. Although having to keep flipping the board upside down to solder components and connect them properly kind of threw me off. I realized I made a mistake by soldering each end of the 220 ohm resistor to the positive side of the Zener diode, which would be connected to the source of each MOSFET, and it's supposed to be connected to the gate. I fixed this by desoldering it and then resoldering it to the negative side of the Zener diode so it can be connected to the gate. The core competency predominantly used in this project is the thinking competency, both creative and critical. I used critical thinking when building it to follow my schematic to put things in the right place so nothing shorts. I used communication as well between me, Tom, and Mark. We communicated often through email to keep in touch on updates and suggestions for the project, and we also held Zoom meetings where we discussed practical objectives of the project and how to make it better. I also used the critical thinking core competency where I had to analyze circuits and use my judgment skills to make a circuit with specific values to get a desired result, which would be to make a powerful enough induction heater. I used the creative thinking competency when looking at similar schematics to small induction heaters and real induction heaters to make my own version. I also had to record a minimum of 30 hours of work experience that tie into this project, particularly the outcome of the learning experience. The experience I feel ties most into my capstone project is my summer job at the P&E, which I worked during August 2022. I worked there for 2 weeks, working a total of 40 hours. I worked in food service, but the skills I learned there were how to listen to other people's verbal instructions, understand them, and execute what I learned myself, as well as to communicate when necessary, such as asking questions about methods and specifying things. I used the communication core competency a lot during the planning and testing phase of my project, where I took suggestions and made adjustments to get a better result and to choose better components for my circuit. During the Zoom meetings with Tom and Mark, I showed my choices of components and they would give me suggestions to change it. These suggestions would be things like look for a capacitor with a higher AC voltage rating, which I would do by looking through DigiKey, which I ordered my components off of, by putting in the parameters I need, such as a specific voltage rating, as well as looking at the datasheets of the components to see what is best for my circuit, which would be the values I used on my LT Spice simulation, as well as what it can handle. I put this wire right here to connect both the sources of the MOSFETs so that they're both grounded, so I can put a negative wire on one of them and have them be both connected. The reason why I soldered 5 capacitors in parallel instead of just using one capacitor was so that there's more surface area available for power dissipation, which is in the form of heat. Also, soldering multiple capacitors in parallel reduces the total effective series resistance. Since higher resistance means more power dissipated, a lower effective series resistance will reduce losses due to power dissipation. These capacitors that are connected in parallel are called capacitor banks. I soldered both of the Schottky diodes to one drain and one gate of each MOSFET. These are fast switching diodes, which help the MOSFETs switch at a quicker speed, reducing the losses during the time they take to turn on and off as the circuit oscillates. The reason I connected my capacitor bank to each drain of the MOSFET using wires is because they can't be connected to the board or else they'll be damaged by the heat. The wires I use to connect them are 18 American gauge wires, and the wires I use for the inductors are 18 American gauge enamel copper magnet wire. I used 20 turns on each to get an inductance of 200 microhenry as I calculated using the inductance factor that was given on the datasheet of the ferrite core. Next, I connected the work coil to the capacitors. I made this using some scrap copper pipe. This is the solenoid that will heat up the conductive material placed in it. The way it works is it will basically become an inductor with the core of whatever is inside it, so it will induce current in whatever object's being heated, if it's conductive. There will be losses from the induced current which dissipate as heat, which is why it only works with conductive material. But the losses also occur due to hysteresis, which only occurs in electromagnets, where the induced currents cause internal friction in the object, which also gets converted to heat, so it works better for electromagnets such as iron. I put the finished product in a cardboard box. I borrowed a DC power supply and an oscilloscope from Vantech to test out the circuit. As I connected the power, I found a problem. The oscilloscope only displayed a flat line. I thought something was wrong with the connection wires, but I noticed the heat sinks became very hot. I used a multimeter to measure voltage and confirm the fact that my circuit was not oscillating. It read 0 across the capacitors and work coils, so clearly something needs to be fixed. I will figure this out sometime in the future. Even though my oscillator did not work, I'm proud of the fact that I built this and nothing blew up. I will continue my education at Simon Fraser University to pursue chemistry. My career goal as of now is something in pharmaceutical sciences, preferably pharmaceutical chemistry and developing medicine. Although I am pursuing chemistry, I have learned a lot about electrical engineering, and it is a topic of interest to me, so I will be continuing my hobby in electronics. Thank you for watching my presentation, and I hope you enjoyed.